Welcome, everyone. So this is another BayesOpt Speaker Series here at Google. And today our speaker is Anastasia Makarova. And very fortunately, because she's at Zurich, and thanks to my colleague Effie, we were able to host her on site. So Anastasia is a final year PhD student at ETH Zurich and working with one of our former speaker, Professor Andreas Krause. And her research is on sequential decision-making under uncertainty, as well as representation learning for structured data. And more recently, she received the Best Paper Award for her work on Bayesian optimization at the AutoML conference. So let's hear what she'll tell us about on her research today. Please take away, Anastasia.
Yeah, hi. Thanks a lot for the introduction. Also, really appreciate the invitation and yeah, being among the scientists I really admire, research I admire. We are going to talk today about Bayesian optimization in the wild. This is the topic: risk-averse decision and budget constraints. Before jumping in this topic, I thought it might make sense just to give you an idea what my research path was about. Yeah, I'm about to finish my PhD, and the essential question that motivates my research is how can we actively learn about the nature? Prior to that, there were like, how can we understand the nature and how can we represent the nature? And basically now, how can we combine them? Talking about sequential decision-making under uncertainty, this is maybe an honest way to say how it looks like, right? And with the path for sure never being linear. Yeah, so active learning, the topic we are gonna talk partly a bit today, arises in many critical applications. And for example, this is drug design, right, where we aim to navigate in a complex space of molecules, right? And very recently, this advances in protein folding, I believe, gonna speed this up. A next example is hyperparameter tuning and control of complex systems. So for example, here, what you see is a Swiss-free electron laser. This is a 700-meter long linear accelerator that enables researchers to observe extremely fast processes like chemical reaction, right? That means that you can also observe molecules turning into each other. And application of this huge machine is again drug design, material science, and such a complex machine should be tuned. Okay, and final example, I think really relevant to the audience today. I don't know, but this is AutoML. A way like how can we create and come up with a proper machine learning model for a particular data set, for a particular application. And I believe that also has enormous impact on other domains, right, wherever we have machine learning models. In these problems, we generally might formulate like a clear objective to be maximized, like compound efficiency in drug design, right, or the energy of X-ray pulse in the accelerator. And these problems can be seen as black box, right, where we iteratively, sequentially interact with the unknown objective. And for some input xt, we observe a noise-perturbed evaluation. And then we navigate this, right, and repeat the procedure, integrating the data we observed. So Bayesian optimization is a powerful framework for such black box, expensive to evaluate, gradient-free, right, functions, and especially in the regimes where we do not have millions of data points, right, but we have tens. And this compact one slide refreshment will just show the building blocks that are needed for the talk today. First, this is the stochastic model, right? This is a model kind of representing the prior over functions. And the second is the acquisition function, the function that guesses good candidates. So throughout this talk, we will focus on Gaussian process models. And these models, they allow us not only to predict, right, the unknown function in the areas we haven't seen it, but also quantify the uncertainty. And uncertainty, particularly two types of uncertainty that going to be relevant for the talk today, which these are epistemic and aleatoric uncertainty. Briefly, epistemic uncertainty is the one that covers any knowledge about the function that we could know, right? But we don't know a priori. And then as we interact with the unknown function, is going to disappear. The aleatoric uncertainty does not disappear due to the irreducible noise. And depending on the problem we have at hand, it's either known or unknown. And if it's unknown, we need to learn it. We measure the convergence of Bayesian optimization in terms of two metrics. As an example of regret and cumulative regret, cumulative computed over the run of the algorithm over iterations, over t iterations. Both have relation to a particular application, right? So if we're talking about tuning a machine or a model in advance and then deploying it to production, we might care more about simple regret. In contrast, if the tuning procedure was happening during the system usage, right, we might care more about how cumulative regret performs. Anyway, for both, we are interested in sublinear regret rate of convergence. Sublinear regret would mean that the performance will converge to the optimal performance at some point. And typically, this bounds, they involve a term which is maximum information gain that measures the complexity of learning the function. Intuitively, like how much can we reduce the uncertainty in the function model, right, when interacting with it. From a finite set of data YT. Okay, so and like if we want the algorithm to be sublinear, right, we also need to show that this information gain is also sublinear. So in general setups, in standard setups, it's shown, and if we go out of the standard setups, it should be shown again, and we will see why we would need it in the next slides. Okay, so this was more or less like the refreshment, right? I really hope I didn't lose anybody. Maybe those who work with Bayesian optimization know it quite well, but these are the ingredients we're gonna need for the talk today. And equipped with that, let's now decide what's the plan, what's the talk gonna be about. And first, we will look into how the aleatoric uncertainty affects our decision, right? An example of two solutions having the same expected value, right? But other moments, for example, but different moments. And an example of that, I will review our paper on risk-averse heteroscedastic Bayesian optimization. Second, we will look into the question of a repeat or not repeat, and review an automatic termination of Bayesian optimization in the context of hyperparameter optimization. I'm also open and encourage you to connect me if maybe after the talk and talk about importance of the domain structure, such as, for example, connection between the variables, or how can we integrate causal considerations. This is, I think, really promising, interesting directions, and I'm happy to chat, but don't have time to feed them in the presentation. So let's now dive into these two first problems. And starting with risk averseness, the work done with great colleagues of mine. In many black box optimizations, we might care not only high utility, but also minimizing risk, right? And in these applications, for example, we might care not only of the pulse, right? But also it being stable, because we do want to observe the whole chemical reaction. Similar to drug design, what we care about maybe the efficiency of a compound, not on a particular set of population, but on the whole population. And when following the standard Bayesian optimization setup for maximizing the unknown function f of x here, we generally would assume a framework where evaluations are perturbed by some raw sub-Gaussian noise, where raw here is variance, or more formal for sub-Gaussian is variance proxy. And the standard GP-UCB upper confidence bound method would implement a paradigm of optimism in the face of uncertainty, right? And it would do it as follows. It would trade off exploration and exploitation, learning about uncertain actions versus choosing actions that lead to high gain. It would do it via GP posterior, mean, and variance. And we focus here on cumulative regret as a convergence matrix. And now consider an example, like GP-UCB is like one of a numerous number of methods in BOR that focuses on expected value only. However, in practice, it might be the case that two solutions, right, like for example, beam positions, they have similar expected value, right? But what we observe is that one is noisier than another. In other words, that would mean that the aleatoric uncertainty we are caring about is input dependent. One way to address it, but partially, is by modeling heteroscedastic noise, just input dependent noise. But that, however, will not change the preferences of the sampling algorithm. And I will show it in a minute or so on a nice visualization. In contrast, what we actually want is we want to make sequential decisions by simultaneously already trading off exploration, exploitation, and risk. And with this goal, what we do, we generalize the framework to risk-averse heteroscedastic Bayesian optimization that trades off mean and input-dependent variance. Importantly, we don't know both of them, right? And we need to learn them on the fly of these evaluations. We reflect this in optimization objective, introducing mean variance objective with alpha here being a coefficient of absolute risk tolerance. So thus we, at this moment, we aim to minimize the risk-averse cumulative regret, right? So such that it incorporates the risk that accumulates through the noise evaluations too. And we do so via actions being selected still via a paradigm of optimism under uncertainty, but we do balance confidence bounds for the unknown function and the noise variance proxy. Okay, so as promised, I'm demonstrating just a possible failure of GP-UCB on a toy and synthetic, but still very illustrative example of the sign function. So here, the unknown function is sinusoid that have two global optimizers, left and right, that call them, but one has much higher noise variance, and here we model it as a sigmoid function. So the evaluations are perturbed by different noise, right? And similar, you can observe when looking into the evaluation of sample variance for the variance proxy. Yes. So this is, again, just an illustrative example, right? But that provides us with an idea that GP-UCB, even when modeled with heteroscedastic noise, so here the model is heteroscedastic, it might tend to stick to the noisy areas. So here what we see is the evaluations, which are red, right? Bold green is the mean, and GP-UCB basically corresponds to the upper bound. In contrast, the idea of RHBO, risk-averse heteroscedastic BOR, is to trade off exploration, exploitation, and risk. And here we see again a similar visualization, and green dotted as our acquisition function. And what we see is that we can actually focus on the areas with lower aleatoric uncertainty, right? And this is basically what we encode in our acquisition strategy. So, and the main takeaway, right, from this nice synthetic examples is that actually the optimizers for the objective, which is just mean, and optimizer for the objective, which is mean variance, they do not coincide, right? And we need to build another procedure for the optimization of that. So that is for sure shown in the paper in a more formal way. Yeah, so all good. Let me now sketch how we implement optimism under uncertainty in practice. So we assume both the unknown function and variance proxy to belong to some reproducing kernel Hilbert space with known kernel, and we believe that we know that they have bounded norm there in this space. And if it is so, right, then we can build GP models for the unknown variance proxy, right? And likewise, we can build the model for the unknown function too. Important and a moment here, which is a caveat, is how we actually provide valid confidence bound in case where the function rho is unknown, right? And we learn it. And here I just mark that actually this model that builds for rho is then used to build proper confidence bounds to navigate the uncertainty for F2. Yeah, so this then both models, yeah, whenever you have a question, just feel free to interrupt me.
Yeah, is there a possibility for using transformations of F to eliminate having to estimate the heteroscedasticity separately? You know, rather than optimizing F, you optimize some monotonic function of F.
I'm not sure I do get your question. Like transfer of F, what does it mean? Like just
so for
basically
example,
learning in advance, right?
Yeah, if you have something
think,
like f of x, where the variance grows with f, you take the square root of f, and you know, maybe the variance is normalized, and you optimize that function instead.
I think maybe like about like how, what else could we optimize? I think let's leave that question just at the very end. So I will get back to this question. Okay. I can also maybe provide you with ideas how actually use transfer learning exactly to make all this sample efficient. By now, what maybe makes sense, like to sum up for this particular procedure where we do focus on learning F and we do care about F, right? And we do care about the variance, right? Because we can optimize whatever we want, right? But in the end, we will implement this model, right, or whatever in the production, and what we will observe gonna be the noise perturbed evaluations, right? So you will, for example, learn AutoML model, and then you launch it in the bank many times, and then what you will observe is also always going to be some noise perturbed, basically realization, right, of this function plus noise. And in that sense, it might make sense then to look directly at this objective, right, and work with that. And basically what I'm showing here is like, yeah, how we can implement such a learning procedure that is easy to implement, right? So here we basically show how to trade off both upper and lower confidence bound for F and rho, both of them like theoretically grounded. And what we show, like another important thing here, is that this algorithm would attain sublinear regret. Why do we care about that? Why is that important? It's because we would know that at some point we will converge to the optimum, right? And to do so, to prove that, we also need to prove that this measure of the complexity of learning, right, this information gain, can be also bounded and is also going to be sublinear for this risk-averse decisions. Yeah, so if you have questions, feel free.
Hi, I just have a very simple question on the setup. So I was just wondering, for the sample variance, are you measuring that by taking repeated samples of the
yes
of the function at one point?
Yes. So this is a really nice question related to also to the regret bounds. Perfect moment to ask that. We do have to take several repetitions, right? Like in AutoML, that would mean that we could learn cross-validation, right? In some other application, that would mean that we need to evaluate the very same input several times. And these bounds that we have, they actually provide a nice trade-off. You can look look a bit complex. That's why I didn't add them to the slide. But they provide you with the trade-off, right? Because the more times you pull the very same arm, the better you model for the variance you have, right? And maybe this better model would improve your convergence guarantees, right? But like on the other hand, you still pay this k times, right, of repeating the very same evaluation. And how to trade off, right, and how to understand like what is the trade-off between paying more for better variance model versus cutting on the costs. That also a nice thing that the regret guarantees highlight. That's an answer.
Yeah, relating to that, when you modeled the rho squared, is it homoscedastic in the sense of at each x you pull it the same amount of time for every x, or is the noise of the variance, basically the variance of the variance, is that modeled relatively uniformly, or?
We do assume it to be homoscedastic, right? So basically we say we will pull each k times, right? And we just fix it, right? This is a fixed setting.
Got it.
But I do believe that, I mean, for exactly as you're saying, for some of the areas where you, for example, already evaluated, right, the variance, it might not make sense to repeat it k times, right? And you can cut on that. While on the areas where it's like underexplored, right, you can maybe have a better estimation of this variance, and you would also build kind of an active model there. I think it just creates like another level of the method. So, but I think in terms of the costs, right? In terms of a particular application, that costs do matter. I think this is a nice direction. Yeah.
Thanks. This is sort of following up on the point that Richard made, and it's about purely like a real-world application. So when you're trying to estimate the variance for a single value of x, that is trivially like you can vectorize it and evaluate it in parallel super fast because it's the same thing, and you can just. On the other hand, if you're vectorizing across different evaluation points, I mean, we all know that when you're doing sequential things, the more points you evaluate in parallel, the more performance degrades. Like it would be best to do one at a time. So if we take into account like a more realistic model of computation costs where it's very cheap and to do lots of replicates at a single point, but evaluations across multiple points might not be as easy to parallelize and might not be like you do that has a cost in terms of how efficient your learning procedure is. Does that change the results a little bit? Because
I think if I can understand you correctly, right, it maybe relates more to the batch setting, right, where you can evaluate more, right? I would say that if we work in that framework, that of course would affect, right? And like exactly how you would, like if you want to evaluate several at the very same time, right? How you would choose them? Like, would you choose them via diversity? Would you choose them by any other strategy? And that strategy of how you choose them, if you want to parallelize a lot, that would affect, of course, the convergence guarantees too.
But parallelizing within a certain point, within a given X, is sort of free to some extent, right?
It depends, right? It depends on what you are doing. If it's a huge control, if it's a huge machine that you need to control, right, and if you need to tune, that might not be the case, right? But true, if you can get it for free, and then your K is just basically unbounded, right? You can just have the raw model as accurate as possible. Then basically in terms of the time, right, all the regrets we're providing here, sublinearity is in terms of the time, right? Then this time this might be smaller. Okay. Yeah, thanks a lot for the questions. I hope that did not distract from the main story. So maybe let's look again what we've just looked at. So this is how the method looks like, right? And the moment we are at is the application, and what I will show you here is hyperparameter tuning of Swiss 3 electron laser. So the main objective there, as I said, is to maximize the pulse energy measured by gas detector, and that might become noisier if we change some hyperparameters, such as, for example, beam position. So what we plot here is the empirical frequency of the true function and the variance. So here is on the left is the function, and on the right is the variance. The values are of course unknown to the method. We start with this violet occurs first. This correspond to GP UCB with heteroscedastic noise. Yes, on these results, it can be already seen, like before we jump into our method, that variance might be high, right? And in comparison to the true value. We further show how RHBOR in the setting would lead to less noisier results, right? Basically choosing F with a similar F value, but smaller noise. And moreover, what we show here is kind of results for different values of this risk tolerance parameter, which is alpha. And by plotting several of them, what I want to show is that with choosing this value, right, which depends, of course, on the user, how they measure their risk, it can help to attain us a good performance between objective and noise variance. Some more plots, again, showing the comparison with other baselines, right? So here we plot variance on x-axis and f on y-axis. And we indeed, once again, show that we can get better result in terms of the variance, right, without without losing much in terms of the function value. Finally, there are two more plots showing the convergence of the cumulative regret. So how it would converge in practice. Okay, so this is more or less it to conclude this part of the talk, where we try to introduced the mean variance approach. I think the main takeaway here would be that we managed to do so, right, and that required learning both the noise variance and the function on the fly. And it's nice to see that you still can get sublinear regrets for this, right? Though the learning procedure becomes more difficult, right? The confidence intervals should be updated, and moreover, practically it performs really nice. And just Also a nice thing that to see how the methods we developed are applied in practice. And here is just a visualization of tuning the machine, which is used widely for production and quality control in semiconductor industry, right? And where it's also important to make safe, risk-averse decisions. And nice to see that it is useful there too. So by that, I would conclude the first part of the talk. So if you have any questions about this, maybe ask them now or just remember them till the second part. Yeah, so I do remember there was a question about transfer learning, right? And maybe this is the best time to address it partially. We do work quite a lot on the meta learning and transfer learning in our group, not me particularly, but it like basically a question is like, why do we need to learn variance every time from scratch, right? If we can basically provide at the very like if we need to repeat the very same tuning every time, why not just to use the model which is meta learned a priori? I think a good answer is like, why not? We indeed can do so. And how basically incorporated, I think it's an open research question, open direction for future for sure. Yeah, so let me know if you have any other questions for this part. Otherwise, we are moving to the second part, and where I'm gonna be talking about a very practical question in sequential interaction, which is limited budget. We will, however, look at that not from a constraint point of view, right? But with an extra decision we need to take, like whether we should repeat the interaction or whether we should stop. And a particular example we're gonna looking into is hyperparameter optimization. And this is the work done with amazing colleagues at ETH and Amazon WS. Back then I was at the internship there. In short, what we propose is a simple criterion that automatically stops the optimization procedure. And in general, this is an important question because in practice, we do not have infinite horizon of data, right? This is in contrast to the theoretical bounds we get in the first part of the presentation. And that means that here we have a clear trade-off between the quality of the solution and the price we pay for that. So consider the following example. We use AutoML like to tune ML model that we will gonna use in a bank, right? And then this model gonna be used for some long time in practice. And the price for making mistake there is high. It's gonna accumulate, and the solution should be like reasonable. The price you pay for the solution should be reasonable in comparison to the mistake price. First of all, that's an extra example for risk-averse strategy, but not only. Here we are looking at this problem from a point of view of the stopping criteria, right? So different banks will for sure have different data, right? And different setups. And that would mean that we cannot just come up with a fixed budget in advance. That would mean that for Bayesian optimization, we would need to have an automatic criterions to stop the procedure. Okay, and yeah, for those who are not familiar with hyperparameter optimization, it can be also considered as black box for everybody else. You can pay attention to the fact that here we change the notation to gammas, so the hyperparameters gammas, and again, some noise perturbed results that we observe. So in case of hyperparameter tuning, for some input hyperparameters, we would need to train the model via SGD, for example, and then we would evaluate the population risk computed for this trained model. So the model that we train on the training data and then predict it on X, and then compute the loss with respect to the true label. And since we're yeah, in the population risk, we care about expectation over the data from the distribution, right? And generally corresponds to idea that we will then launch it and the model will work quite long, right? So we will look at a lot of examples from the distribution. Yes. So again, what we observe here is then the noise perturbed value. What the noise is about here, like where the stochasticity is coming from, it is coming from stochasticity of model training from SGD. And yeah, basically this is the objective we would like to optimize. And yeah, Bayesian optimization is widely used for hyperparameter tuning, and you might find it in many line tuning services. And as we know, as we've seen in the previous part, as we know from background, that the function f, how we would look for the optimizer, a known optimizer, we would again build a probabilistic model that importantly here I depict in gray. And then we would select this promising next hyperparameters candidates via acquisition function. So this iterative search would generally last till the budget that was predefined in advance. And the metric that we care about here would be the simple regret, right? So in theoretical setup, we would maybe care about cumulative regret, right? But here we care like how actually the model is performed in the production. So that's why we focus on simple regret. And yeah, so importantly, here in hyperparameter optimization, what we actually can optimize is not the population risk, right? The data distribution is actually known in practice. And what we can optimize and we can evaluate is just an estimator of population risk. So that is for some data that we divide into train, validation, and test. We evaluate the performance on the validation set, right? So this for some DV here, and what we observe as evaluation gonna inherit stochasticity that comes not only from model training, but also from the data realization that we have for the validation set. Yeah, quite an obvious fact that, however, highlights the discrepancy between what we would like to optimize, right, and what we can optimize. And that is not only a problem that appears in optimal, right? It can happen in wide setups too. And at that moment, maybe let's focus on the visualization that's gonna give us a hint in the future for the method. So we apply now Bayesian optimization for the computable target, which is in orange here. And iteratively, we converge to some solution, right? Again, the quality is quantified, the convergence quantified in terms of the simple regret. And the problem is that inconsistency of the objective might result in yielding suboptimal solution to the initial problem, right? To the population risk. Yeah, just imagine, again, the situation with the bank. We've invested a lot of resources into applying Bayesian optimization to the commutable target, and then we implement it, and then what we observe in practice is actually not satisfying. And this is basically the first empirical result of the paper, showing that overfitting with respect to the validation data might happen, meaning that longer optimization might not only waste the resources we have, right, but also harm the generalization performance. There are different ways to solve this problem, right? This overfitting problem. And one way would be just maybe collect more representable data, right, about the users, maybe also take into account distributional shift if we can measure it and quantify somehow. Yeah, maybe even go for distributional robustness viewer. But here, what we are trying to focus on is more simple solution that can be used out of the box, right? Because of all the methods I've mentioned, sometimes they require a lot of extra computation. And what we propose here is to deal with the stopping criteria is to introduce the stopping criteria that would basically characterize in the following informal rule, stop the procedures while once we are unlikely to improve the population risk. How can we measure that? And so we can look actually what happens if we optimize this estimator instead of the true function. So let us look again at the visualization and notice that because it is an estimator, it is equipped with uncertainty, right? And here I depicted in orange. More formally, that means that if we know that the estimator error is bounded by some epsilon st, we can show that the regret of the true objective that we are interested in can be bounded. It can be bounded in terms of the statistical error of the estimator plus the regret that we observe via optimizing. Not observe, but the regret which is for the computable target, right? The one we apply Bayesian optimization to. Yeah, and that is an important inequality because it shows that even if we reduce the error and the regret to 0, as we've seen we could do right from the previous part of the talk, theoretically it all can be achieved, we cannot improve beyond the fluctuation error epsilon st that is already encoded in the estimator. And that's why that's what actually motivates the stopping criteria we have introduced. An idea is like basically to stop when these values are comparable, and comparable in our case empirically decided it's going to be the values not of order 10 or 2, but just comparable. And formally that would lead to the termination criteria saying that that once the simple regret is dominated by the statistical error of the estimator, then we stop. So this is a very simple idea, right? It's easy to use. It is interpretable. However, neither the regret nor the error are known in advance. And these are the ingredients. I will explain how we estimate. Yeah, so the upper bound on the regret can be naturally extracted from the confidence intervals. That is, for some computable target, orange, that we have here, as we observe the points gamma t, we get the posterior GP, right? And then as long as this confidence, as long as our model is well calibrated, we can use lower and upper confidence bounds as bounds for the estimator. So and then let me now show how we can use this bounds to get bound for the regret, particularly at iteration t. What we are trying to get is what we can compute is the minimum over the whole domain of a lower confidence bound. This is basically corresponds to optimizing the acquisition function, right? So as we would apply it for in a GPU-CB framework, for example. And then for each of the points that are over the domain, we can compute the upper bound on the distance to this minimum, right? And that would mean that we would just need to compute difference between UCB and this value that we just computed. And so the value of interest that we want to use in our bound is then the minimum over all points that we have observed so far of these distances to the optimistic minimum, let's say like this. So this is basically the way we estimate this regret, right? And it's already enough to like use in a stopping criteria if we can come up with a nice threshold for the stop. Yeah, but basically for the accuracy of the model. But I will also briefly talk about how we can estimate the error of the estimator, that is to make it fully automatic. And we do consider a case of cross-validation, right? This is the characteristics of which are well studied. And if we're talking about bias and variance, right, we can say that the bias can be neglected in terms of in the case of the cross-validation, and the variance can be estimated. And getting back to our framework with HPR, hyperparameter optimization, if we work with k-fold cross-validation, and this is their mean as something that navigates our optimization procedure, then the sample variance that we get from this fold is something that we can get for free. And then this sample variance is then used to get an estimate for the variance of the estimator. I believe it might sound difficult, complicated, right? Variance of variances, but basically what we are saying is that the variance of the estimator here going to be somehow related with the constant term that depends on number of folds, and the sizes of this fold will be related to the sample variance. So this is something that can be used from the literature. That concludes basically both the ingredients of the stopping criteria, and the only results I will show more in the paper are the results for XGBoost and random forest and tuning hyperparameters with Bayesian optimization there. And how do we compare the method? We do compare them in terms of the speed up, right, and in terms of the error change. And to this end, we introduce relative time change, which is an x-axis, and larger means we have more speed up, and on the y-axis we have test relative test error change, and positive means improvements, negative means you actually harmed your model. And after stopping is rather unexplored area, so the baselines I'm going to be talking about, they are quite naive still, they are used in practice. So convergence, first baseline is convergence, and is triggered if we observe that the best observed point haven't changed for some particular number of iterations. This further two relates to probability of improvement and expected improvement once they fall below some threshold. And finally, we plot here our method with these threshold computed from cross-validation. Similar results for random forest and tuning the parameters there. Maybe the main takeaway message from this plot is that if we pay attention to how the dispersion over the time change look like for our method and for others, you will see that it's kind of wider, right? In contrast to the test error change, which is much smaller. That shows that the method actually adaptive, right? So we do not stop when it is not useful, right? And we do stop when we can gain something in it. Yeah, so and that basically it for that work too. So maybe takeaway for practitioners is like being careful about overfitting to the validation data, right? And that it like important thing that the discrepancy is observed in HPOR and in BOR, and that's why you can use this adaptive termination criterion. I think it's a very preliminary work, right, of what can be done in automatic termination for Bayesian optimization. In here, just the several ideas might be interesting. First one is that this estimation of the gain, right, of the regret, sorry, estimation of the regret, it might be used not only in AutoML, right? And it might be the case that the computable target is known to be just a proxy for the objective. And if we know it happens, then we could always think about how we can basically exploit this to cut on the resources we spend. And the second idea is that just basically relates to the first paper we have today is like, what if we do observe some heteroscedasticity in the aleatoric uncertainty, right? And then basically, how can we combine it with risk-averse decisions? Yeah, so by that, I'm concluding the talk. So these are the topics we've looked at, and some other topics I'm happy to chat about and answer the questions. So feel free to ask any questions now, or just reach me, ping me somewhere, and I'm happy to discuss them. Yeah, thanks a lot for your attention.
Great. Thank you so much, Anastasia. And it's really interesting to see like how heteroscedasticity and early termination can bring like a lot of value to Bayesian optimization. So could you unmute the room and increase the volume of the room and mute your current laptop?
Basically, the moment.
Okay, great.
To
So
yes.
To everyone in this call, if you have questions, please raise your hand. All right, so I actually have a question, and I'm really curious about. So in the settings of, for example, hyperparameter tuning, typically, or like at least in some cases I've seen, people care more about the actual observation. So eventually, like what we are like showing in like the final results, or sometimes, okay, what's the input that achieves the best observation? So I'm wondering, like, what does that mean to the risk-averse decision? Does it mean like we're gonna be more risk-prone? And also, like, what kind of implications does it have for early termination?
So this is basically, am I understanding you correctly that, again, what we're talking about, like how to connect them, right? So if we not only care about the expected performance, right, but if we do introduce the aleatoric thing, like how the stopping criteria would work. I think it's a nice question, right? So this framework on automated stopping is just uses any function f, right? Like we do not specify what the objective is, right? It's just an objective, and we know it is like here at estimator for that. And in a similar spirit, we've changed the objective in the risk-averse risk-averse setting. We can also say, okay, now we do focus on mean variance. Let's try to think like what would be the statistical error, right, between estimating, basically when we evaluate not the true mean variance, right, but only at estimator, what would be then the properties and what would be the distance between two of them. And I think this is a very like solid way to do so, right? Because it provides you with the framework, and now you can choose what objective you care about. What do you think? Does it answer?
Kind of like about what the model is and what exactly is the objective. So whether it's like the difference between the function, well, the underlying function values itself, or like the observations. Yeah, but I think perhaps in that case, it's going to be like a more risk-prone option, which is kind of interesting to think about.
Yeah, yes, I agree.
Yeah. All right. Any other questions from the audience? All right.
Yeah.
Yeah, I think we also cover some questions along the way. So if not, we can conclude the talk. And thank you so much, Anastasia, for the really interesting talk. And thank you, Afi, for hosting. All right,
Thanks
so
a lot.
that's it. Thank you, everyone.
Thank you. Thanks a lot for coming.